Welcome back, Math Mule. Today I'm in a very nice setting in nature, and I'm very excited to share with you a very fascinating result in group theory. Now, before we start, I want to mention that I made a higher quality animation video, and I will be doing those around 1 to 2 times a month because they do take a lot of time. And I will be posting these more casual videos every 4 to 5 times a month. Okay, now what is the result I'm trying to prove? It does require a bit of group theory knowledge, but I will cover that in a different video and all the terms you need to know. So let's say we have a group G, okay? And let's say the order of G, which is the number of elements in G, is equal to a prime. This implies the fact that G has a prime number of elements implies that G is cyclic, and that is a very powerful result. So to do this, we need a very powerful result in group theory. The name is of Lagrange. And what it says is that for any subgroup H, that's a subgroup of G, then the order of H, which means how many elements are in H, divides the order of G. So for any subgroup, the number of elements in that subgroup must always divide the number of elements in the total group. Okay, so using this, we can immediately see the connection between the prime number and the order of different subgroups. So let's say, we have the group G, and it's equal to some prime. Now what are the prime factors of this? Well, there's 1 and p. These are the only divisors. Thus, if there is a subgroup H, then H must be of order 1 or p, because those are the only numbers that divide p. And thus, for a subgroup H to exist, the number of elements in H must be a divisor of p, so it must be 1 or p itself. But this implies that H is equal to the trivial subgroup, which just consists of the identity element in G, or H is equal to the whole group itself. So there are no non-trivial proper subgroups of G. And all that means is that there are no subgroups that are not the trivial subgroup, which is just the identity, and that are not G as well. Because the trivial subgroup, consisting of just the identity, and G is a subgroup of G, these two subgroups are always subgroups for all groups. So we're not interested in studying them. So all this is saying is that if we have a subgroup, there's no subgroups that are essentially interesting. It's either the trivial subgroup, so just the identity, or the whole group itself. Okay, so now how do we prove that G is cyclic? Well, let's fix an element A in the group G, and A does not equal E. Well, first of all, we're allowed to do this because G has a prime order, and primes are greater than or equal to 2. So there's at least one other element other than E. Okay, now let's consider the subgroup generated by A. This denotes the cyclic subgroup generated by A. Essentially, this just means A to the n for all n in the integers. So it's essentially the subgroup generated by all powers of A. And this is indeed a subgroup, you can verify. So we have a subgroup in G. But we said that the subgroups of G either have order 1 or p. But note that the order of the cyclic group generated by A does not equal 1 because we chose A to not equal E. In other words, the cyclic subgroup generated by A must have at least 2 elements because A does not equal to the identity. We have that order of the cyclic subgroup does not equal 1. But that means there's only one option left. The order of the cyclic subgroup must equal P. And therefore, the cyclic subgroup must equal G because G has order P. So we just proved that there exists an element such that all finite products of that element equals the group G, and that's the definition of cyclic. So there we go. That's the proof.